So we're going to jumpstart our session Tuesday, 29 August. This is CSC239, Scientific Computing Applications. Welcome, and what we'd like to do is to walk through a quick review of our student learning objectives for the first module, and then to take a moment just to call out some things with the first round of assignments and our solution. I want you to note that if you were able to submit a valid artifact of a rental or purchase of our textbook, that you'd be able to read chapter 1 and then sections 2.1 through 2.3 and section 3.1 of chapter 3. So we're gonna identify specific areas in that textbook to reference, and this is relevant to our current objectives for the module. Our first module is about scientific computing origins and the essentials. And some of this may be a review for some of you, but I'm hoping that I can pique some curiosity even for upper level computer science students. I hope to present some things that you've never seen before or considered before, just part of the value added thing. So we're going to be talking about data management before data analysis. In this module, we're going to call out Excel as a model or template for what you're going to do, regardless of the software or application that you would use for scientific computing. Now, when we say scientific computing generically, we mean capturing data, analyzing data, identifying patterns, perhaps performing some modeling. So there's a broad context for scientific computing. But that doesn't mean that we have test tubes and beakers or microscopes. We may have those kinds of things. We may have plenty of scientific instruments, but there may be other sources of data input that we are conducting an investigation of, and it could be data analysis of internet traffic across a certain network interface, right? So there could be all manner of contexts and scenarios and a wide range of research interests that could be casual in nature. You're doing basic troubleshooting, or they could be very highly formalized. So we are going to talk a little bit about the scientific method and its process along the way. We've already talked in our sessions last week about using a virtual machine. And there is one thing I wanted to call out about our assignments. So the second assignment has to do with optimizing your personal technology. And the thing that I would call out to you right here and right now that's most important is this idea that if you optimize your personal technology, you should have about 40 to 50 gigabytes of free hard disk space available on your machine. One of the things that you have to do when you're performing the tasks for the host specs and you're optimizing is that you have to include some detail about your drive. And so what you'd do is you'd open up File Explorer as I have here. You would click on where it says this computer or my computer. And then you would take a screenshot of where it clearly shows, okay, I have, and if these drives or the C drive doesn't show, you'll have to scroll down. So your screen may be different and you don't see the drives and you have to find it and then scroll down and click elsewhere before you can display the drive like this. You want to be in details view because that's going to be easier to parse out. But if you don't have it in details view and you just want to take a screenshot of this, whoops, I'm sorry, we had list, I think, medium icons. One of the views we had just a moment ago showed the capacity. Everybody remembers that, right? So if your view does not show how much is free and how much is available, the total disk space here you see is 928 gigabytes and I have 655 gigabytes. In order for you to engage the solution for module 1, you must have adequate hard drive space. And you can pull this off with about 30 gigs if you were cramped. So if you were working with limited hard drive space on your laptop, you could take some videos, you could take some movies or some stuff that you have in there, lots of graphics. You could move some of that data temporarily out of the way to make room, but you'll need 30 gigabytes of free space. And that's really important because before you engage 1.4, we want to take a look and make sure you don't crash the system. So you have to be sure if you lack 30 gigabytes of hard disk space, and then you try to engage, it's 40 is the safety measure. You have a 10 gig file that you downloaded, and if you don't have 30 gigs there already, by the time you start importing it, it's going to suck all that in and then take up 10 more gigs. Then it's going to unpack the virtual machine. The virtual machine takes up 20 gigs after it expands. You're going to need a little bit of breathing room. So at a bare minimum, around 32 gigs is the most you could cut that. In previous seasons, it might be higher this time. It'd be better if you had 40 or 50 gigabytes. But that's one thing I want to call out intentionally. So be sure that when you finish 1.2, one of the artifacts you turn in will show how much free disk space, and you do not want to proceed. I'm actually going to put a caution out here on the virtual machine setup, big yellow tag that says, important, be sure to affirm or confirm that you have a minimum of X number of gigs of drive space before you go ahead and finish this, and what to do if you don't, right? Any questions about our assignments or the solution at this point?
No.
Okay, so we have a traditional study guide for the learning outcomes, and if you open that up, if you click into here and then in the references, the recordings from last week are now in resources under class recordings, under fall 2023, and they're listed in reverse chronological order from the most recent and older. So as we finish today, I'm going to be pushing out the introduction, Scientific Computing Essentials, right? And it'll have today's date on it, and it'll be at the top of the list. So as far as your references, go into the references, you'll see the study guide revision 1C, the module 1 study guide addendum, and then there's something to kind of cue you into some things about the assessment before you take the assessment if you've never had the previous experience of being in one of my classes, okay? Let's take a look at our study guide. So here it basically says, be sure to read this part of your textbook. That's really important. Let me say it again, that's really important. And since it's in the study guide, the content in those very specific sections, it's part of the review and part of what we're doing. It says, describe the essential scientific computing abilities expected of STEM professionals. And then the student learning objectives that follow really kind of go together. When we get down to contrast how variable names and the assignment operator differ from use in mathematics, right? Identify, label, and provide the function of primary hardware computer components. Explain how best to organize the important criteria required for a scientific computing application. So whenever you see SC, that's short for scientific computing. If you see SCA, that's an abbreviation for scientific computing application. Any questions so far? Can somebody unmute your mic and let me know that we're still in the loop?
Yes.
Now, this is a big one right here. So of all the things that scientific computing professionals, there's some blinders. It's all about the experiment, it's all about the data. But when it comes to the computer, there are some specific things that get left behind in the dust almost always. And this is an industry thing. So there's a gap that I'm going to call out, several that I'm going to call out, and I'm going to say, oh, your life will be so much easier if you work in this manner, as opposed to what you see, for examples, in the textbook. That'll be clear as we engage that. What I'd like to do now is provide a quick, I'd like to provide a quick overview of the first few learning objectives with a separate presentation. And this is a presentation that was prepared a couple of years ago, originally for ECS Scholars. Some of you may or may not have experience with the ECS Scholars program. But what I'd like to do is go ahead and kick this off. And this is a good way to sort of get a feel for those first few student learning objectives. I'm gonna So we're going to conduct a quick overview of computer architecture and the two types of digital information. We're going to, now when I say the two types of digital information, for those of you that are more advanced in computer science, I'm not talking about data types. I am talking about types of digital information. So I just wanted to clarify. The significance of base 2 and binary values, the Boolean revolution. There's something I call the dynamic duo and a hat trick. So a hat trick is like 1, 2, 3 Musketeers, or 3 scores, 3 goals in a row. So you have like a win-win scenario with scientific applications. And there are cases where you need to really pay close attention to 3 specifics, right? And I referred to the term elements and statements, right? Origins of procedural programming and the new and improved method. So back in the day, 50, 60 years ago, we had mainframe computers, and the way that you coded was step-by-step in a linear fashion. It was called procedural programming. Now we have object-oriented methods, and that's supposed to be better. Yeah, it depends. If you don't do it right, it's not really better. The secret sauce of coding made it easy. Now, this is one thing that I would love to insist is part of every introductory computing science course. Anything that has to do with applications that involves variables. Because there is something about that, it's one of those gaps. And if you do this, then it's kind of like a secret ingredient that makes you a rock star with your coding, because it just works, and I'm not exaggerating. And then when I was in industry for 25 years, and I hired programmers to create enterprise integrated solutions for the entire organization, I would often require them to do this, and they'd groan and they'd moan and they'd say, I really don't, I'm not feeling it, right? And sometimes I would fire people because they wouldn't do it, right? So I thought it's worth mentioning here. Pseudocode is a foundation for prototypes and production coding. So you may have heard the term pseudocode. We're going to examine that for a brief moment. So let's look at basic computer architecture. This may be a quick refresher for those of you that have had CSC241. For those of you that are in CSC241 right now, you're about to see this. The basic computer architecture in terms of hardware is relevant because when you're creating applications, you want to understand the equipment that it runs on and therefore the limitations. Because if you code in a certain manner, you can use up or exhaust the hardware limitations too quickly and then have problems. So every computer basically has a processor. You probably already knew this. It's called a CPU, a central processing unit. But there are 3 primary components in the central processing unit. One of them has to do with math. It's called the arithmetic logic unit. There are memory registers, and there's a control mechanism, a controller in there, right? And so that kind of controls what's being done and in what order, and that's its function. Basic computer, any computing device has these, by the way, from the largest supercomputers down to a smart device in your home, a smart TV. Your smart TV has this same thing. And the $10 million supercomputing, the new edition at Sandia, that also has all this, right? So memory. When we talk about memory, we're talking about volatile memory. The memory that's referred to here is RAM and random access memory. It's temporary memory where it's your workspace. I want you to think of it as so one analogy you can use for computers is to think of it as a workshop. And you are the CPU. You would be the person who is working process with tools and materials, if this was a workshop. So if you're the craftsman in the workshop, you can think of yourself as the CPU. Is everybody okay with that so far? And think of yourself as a very capable CPU. A CPU with lots of cores and abundant cache, static RAM cache, right? So there are all sorts of performance things, and some people get into that a lot. But the memory, the RAM, is like the workbench. So I want you to think of random access memory as the space you have to work your stuff. Tools, process, materials. You are the CPU making all that happen, but you're kind of cramped if your work table is this big, right? Does everybody understand what I'm saying? But if you have a work table that looks like this, okay, so if I stop sharing here for a second, if you have a set of work tables like this, can everybody see this?
We can see the classroom.
Yeah.
Okay, so this would be like a computer that has 32 or 64 gigs of RAM. And if you were the CPU, you could actually, if you think about a multi-core CPU, that's like having a married couple in the room now, and they're both doing things with their hands, right? Material, process, they're working, they're doing things with raw materials and whatever it is you're producing in your workshop, okay? So there's more space. The more RAM you have, the less work your CPU has to do when you're trying to get something done. Now, if we shrunk this down to a single table, and we had two people working, like we had a dual core or a quad core processor, right? Let's say we had a pair of people. They would both sit here and they'd start working, and what would happen? They'd start stepping on each other, right? So what would they have to do? They'd probably have to take some of their materials and their tools and put them over here to the side separately. That's where the input-output comes in, okay? Now let's talk about input-output for just a moment. Input-output, and maybe you've never heard people talking quite that way about all this, but hey, okay. So input-output, we have a device that is also memory intensive, but it's permanent memory. And the permanent memory that we're talking about here is the hard disk or SD card, right? So if you have a phone or a tablet that has an SD card, that's the equivalent of the hard drive. If you have an SSD drive or you have a traditional hard drive on a laptop or a PC, the input-output to that disk, that's permanent memory, persistent memory. That has the data and information and the instructions have to go and be loaded into the workspace, into the memory, onto the workshop tables in order for anybody to be able to do anything. Now, if you run out of space, what you have to do is park. You have to temporarily put aside in bins. So you have storage bins around maybe. So when you run out of space, you're going to be like offloading some tools and material until you have room or you have the means to do it again. And then you're going to go and fetch that. That's the same thing that's happening with the hard drive, okay? So input-output also includes things like video displays, keyboards and mice, right? Microphones. So input-output can be in both directions, or sometimes input and output is in single directions. The most important input-output device in a computer would be the boot disk or the hard disk, where the original startup instructions can load. And without that, you really don't have anywhere to go. Kind of like the battery of a car. You turn the key, without a battery, you can't get started, right? Any questions about our architecture? So data and instructions. Now this I'm calling out intentionally. Notice the red circle. This doesn't seem like a big deal. But the first time computer scientists figured out how to store the digital information and the instructions on how to operate on that data, that's when the magic started to happen. So that was like a tipping point. It was like discovering the critical mass for a fission bomb, right? Where we could save 500,000 Japanese lives and 25,000 American lives. So if you do the math, we dropped a bomb on Hiroshima and Nagasaki, and there's a lot of controversy over that, but it was very clear to experts that the loss of life for conventional warfare without the superiority of that firepower would have dragged on, and it would have been horrific. There would have been many hundreds and hundreds, perhaps 1 million civilians, and I think the numbers were actually higher. It could have been as many as 250,000 servicemen and women dead, and 10 million Japanese dead, because they were going to fight to the death, right? Now, that's a side story. I don't want to get too distracted. The point is that you have to have these components come together, and unless they're there, like spark and gasoline and air in a car, you're not going to go anywhere unless you have the right stuff. And the important thing to remember about the RAM is that there has to be enough room, not just for the data, but also for the instructions. Otherwise, you got to go to the hard disk all the time, all the time, all the time. And that's what happens when you have a device that has an application to run that's too big for the available memory. Everybody understand what I'm talking about? No room in the end. You design a scientific computing application and it's just too big for the space you're going to run it on. That's why we're covering this. Okay, so computers can only handle 2 values. You probably already know this: on and off, open or closed, true or false, yes or no, ones and zeros. So why is this a big deal? Well, the thing that you need to understand is this part right here: the true or false, yes or no. The true or false, yes or no condition for having a 1 or a 0 in digital terms, it's those 2 conditions that form the basis for which logical decisions, breakpoints, right? You can have, does temperature exceed 80 degrees? Yes, we do this. We turn on the AC. No, we don't. We leave the AC off. It's lower than this, right? So the logical decisions, these are the precursors of any and all programming languages. Without that logic piece, you really have a calculator that can do stuff with numbers, and that's it. But once you enter the logic piece, now you have a powerful component. It's like having the gasoline, but no spark and no air. You can actually take a full pail of gasoline, light it, and if there isn't much air in the room, it's not going to explode. It's going to flicker a little bit and then go out. It's pretty dramatic to see that. I wouldn't recommend doing that just off the cuff, though. Any questions?
Nope.
So I'm going to advocate for those of you who are in our course and are not computer science students that you adopt sensible coding skills. We want you to, a sensible process to develop coding skills. And there are a couple of things about this that I'm going to I'm going to be out in left field. And when you go online, you're going to look for the same kind of information. You're going to go, Professor Kentop is whacked, because I don't see this anywhere else in a textbook. And that's because we're starting to realize some things about barriers to young students in particular, working and having accessible access to computers because of some barriers at a certain knowledge threshold, right? Our students, we want students to be able to start computing before they can do algebra. That's ideally what we want, right? So the thing I want you to understand is that when we're talking about a programming language, have you ever wondered about the word language? It's a programming language. And yet, when you see this stuff written out, doesn't it look like algebra? I'm just saying, doesn't that seem odd? A little bit, right? Okay, so there are other things that we don't call out when we start teaching programming and coding, and it's almost a crime. So here's a big one, right? You're supposed to read the programming statement from right to left. By instinct, we always read from left to right. When we look at a programming statement, we're in the habit of starting on the left because that's what we do with sentences, or that's what we do in math. We read from the left to the right. Now, there may be some right-handed people that work in reverse, and they would have a jump on everybody else. The thing to remember is that you should take up the habit intentionally of always looking at a programming statement from the right side. I want to make sure that I'm not, when I'm gesturing, is this the right side? Is that the right side for you? Are you seeing this on the right side or the left side? I'm just asking.
The right, seeing you.
So this is my right side.
Oh, yeah, that's right side. Oh, okay. I thought you meant like the side of the room.
Do you want to work from right to left? Is how you want to do the reading. I didn't want my gestures to confuse people.
Sorry. No, but that's your right hand, yeah.
Okay. Now, when you create statements, yeah, you want to create them and review them from right to left, because what's happening on the right side is that there's a condition and a process, and then the result ends up getting stored in something on the left. And that's counterintuitive. We don't call that out. When we sit down to teach people programming, they're like, okay, let's make a programmer, let's make our first program. We're going to create a variable, and it's called hello. And then we're going to store hello world, the text, hello world, in the variable we call hello, or maybe we call the variable x, right? And then we print the contents of the variable so that it displays to the screen. And that's kind of a backwards, and I'm using that term intentionally, so I'm going to repeat it again. It's not vulgar, but it kind of hints. It's sort of a backwards way of doing things. If you really want people to get coding so it's easy for them and it's intuitive, we got to unlearn some things. So you've been taking years reading left to right. Yeah? And you've been doing math from left to right. When you solve equations, you've been doing chemistry from math to right. Here are the products. Here's the reaction. Here are the reactants on the left. Here's the reaction. Here are the products. My apologies to our chemistry faculty. Okay, everybody with me? We're in the habit of doing it from left to right. And you have to intentionally think, okay, I'm going to work differently. Here's the second. Everybody get that, right? Now, I know I said that over and over again, but you're going to see why that matters in a minute. You're going to see why that matters in a minute, and I'm going to prove to you that it is so important that if you don't pay attention about right to left, you can blow up a $300 million spacecraft and end lives, because it's already happened. I will show you the results of what happens when you lose sight of that, okay? Any questions before we get into the logic piece? Questions, comments? Okay, logic. Logic involves a condition or case that's presented where the answer is either true or false, yes or no. Right? Everybody with me? So that true or false, yes or no condition can be represented by a 1 or a 0. And that allows us to test for certain conditions. And if it's true, yes, we do this. If it's false, no, we do something else. That's like the transmission of the motor that makes programming work. Without logical conditions, we have no way to translate the arithmetic capability into something that's meaningful beyond raw numbers. And I know that's a pretty bold statement, but it's the basis for decisions that trigger selected coding statements. So based on a condition, you can execute this instead of that. And that's huge, right? Any question about logic? We're not going to cover logic to the point where you wish you had taken a course on logic, but in case you are a Bachelor of Science or an Associate of Science student and you need to find some humanities electives, might I recommend in the philosophies department the course on logic. And you'll find out that it's a different kind of logic, but it does tickle that part of the brain where you start thinking more logically. So just a thought. Then there's indispensable components. I would call them like the internal parts that make the transmission work. Things like inputs, process, outputs, keywords, operators, right? So you have gear shifts and steering wheels. These are the equivalents of the programming language, and syntax. How, what it means, and in what order. The syntax is the kind of step-by-step, this is what I do to drive a car kind of thing. Those are the indispensable components of any programming language. Now, if you understand that this is the stage that's set for coding to work properly, let me say that again. If you understand these are the elements that you need in order for coding to work properly, you're not going to cut corners. And I'm talking specifically to computer science students right now who have had years of working a certain way, and you know who you are. And what? You go to a Code Warrior site online, right? You know what I'm talking about. You go to GitHub and you get some and you turn it in and the instructor goes, what does this statement do? And what are these variables? And you're like, I don't know, right? The point I'm trying to make is up to this point, you've been indoctrinated, almost like basic training, drill instruction on how to do coding in a certain manner. But I'm going to challenge, especially my computer science students, to change the way they work in very simple but profound ways. And I guarantee you, it will save your job. It may save lives because the code you write will work differently and better than anyone else. And I know that's a bold statement, but when we talk about computer languages, programming languages, it is a language, it is not math. It's going to look like math, it's going to look like algebra, but it's not. To prove a point, I'm going to try to show you an example of how crazy things can get if you don't understand that important distinction. Now, before we get into that, I want to talk about this dynamic duo. So adding Boolean logic to coding statements is like adding concrete and water to sand, right? If you have a condition you can test where the outcome is true or false, notice those come in pairs, right? That's the dynamic duo. Condition that can be tested, and the answer can be true or false, right? You have pairs of important elements there as input for decisions, right? You can branch or jump in procedures. Now, I like to refer to these primary components of coding statements as the three musketeers of coding statements, right? There are just three coding statements that perform the real work of any method or module or function. So I'm going to kind of put this in plain terms for people who were traumatized by coding boot camps, and they had a lot of stuff on the screen, and you just had to scramble to just copy the same lines with the same characters. And if you were good at copying the same, does anybody feel what I'm talking about right now? You know, like you went to your first coding class or you went to your first coding boot camp and they sat you down and the instructor goes, oh, I'm going to show you something really cool. And you're going to write this and it's going to make the robot do that. And you're like, oh yeah, let's do that. Then they put it on the screen and you have to do exactly what they do and how they do it. And if you don't have the characters and the number of spaces and the punctuation just right, doesn't work, doesn't work, doesn't work. Am I preaching to anybody here today? Are any of you feeling anything about what I've just stated?
I mean, I know you like the expression, like people who want you to enjoy it like they do. I understand that. We have people that really enjoy coding to
Yeah,
express themselves
they
that way.
understand the power of it. And they're
Yes.
advocates, they're evangelists. But the problem is that we kind of fast track our most basic students without explaining a few things, right? So there are 3 coding statements that do all the work for every application you'll ever build. The first one, the first of the coding statements are called sequence statements. Now they handle things where there's a flow and order. Now that's just intuitive. First you're going to capture this input, then you're going to process it that way, then you're going to deliver the output to this screen or that printer or whatever, right? It's kind of basic. Everybody knows that. But then there are decision statements. And those are, a lot of times there isn't a whole lot of thought given to decision statements. Like, okay, and the more you think about decision statements as a category of coding statement, one of those 3 musketeers, it's like, this is one of the neglected ones. You know, you want to ask yourself, is there a condition I can test for? Is that important? Would it make my software more usable? Or is it only ever going to do one thing? And it requires somebody to click a button. So it'll do something, but only if somebody clicks a button. Only ever. It takes human interaction. Put another way, unless somebody does something, it's worth less. Okay? Now, I'm coming at this from a whole different angle, but I worked in industry for 25 years, and if I had a dime for every computer science major that graduated, and I'm like, okay, let's work some basic stuff. We got to have an application, and it has to do this. It's like these are the finer points that I woulda, coulda, shoulda insisted on 25 years ago. So, all right, repetition statements provide the means for automation. One thing that computers do in rapidly aggressive manners, they're very, very good at repeating things. So if there's something that requires a chainsaw, a lot of little bits, a lot of little teeth chewing up something, computers are an ideal tool for that purpose. But you have to understand when and how the repetition statement should be engaged. Put another way, there are people who code simple statements for a basic program and they leave the door open and hackers love you. Those of you who do this. Because they don't have any safeties in place for that chainsaw. It's kind of like crossing a chainsaw with a Ginsu knife. So then the person who figures out how to yoke your application has turned it into a weapon because they have that part of your code running all the time, even when it's not supposed to run, hence the need for decision statements, right? Now, a lot of this is going to be a lot plainer and easier to understand once we start working with practical examples, okay? Why don't we take a short break and let's stand up and stretch, because I promised that we would take a break at some point in our class. And this week I want to start doing that. So what I'm going to do is I'm going to stop sharing, stop recording. I'm going to break out of the Zoom room. Let's take like 2 minutes, all right? And then when we come back, I'm going to show you how to prove that 2 equals 1. And I'm going to ask you if you know how that mistake happened. We're going to walk through it together. We're going to use math. We're going to use it wrong. And we're going to prove that 2 equals 1 on the other side of our 2-minute break. Okay? Any questions before we break?
No, sir.
Okay.